Alrighty, good afternoon, welcome. We're nearing the fag end of the class. Just the link layer chapter is left. After we wrap up the routing today, like I said, we're running almost 2 classes behind, so I really don't foresee that you'll get to see much of wireless, if anything, in this course. Usually I spend a couple lectures on wireless, but I think partly because of the class size and more time to clicker questions and such, we've been going a little bit slower. So just like in the previous chapter, I'm going to have one of the components, the SDN control plane as DIY, read it yourself. It's mostly general knowledge, just facts and knowledge about a rapidly changing technology landscape. It should be fun reading, but a lot of it is already a little bit outdated. It's not the kind that lends itself to critical thinking questions. So those are the kinds that I tend to read for DIY. Today we're going to see something very important. Inter-domain routing. Routing is one of the most critical functions of the network layer. The network layer is architecturally the most significant layer, I would say, of any network architecture or network design. That's central to the DNA of what the network is. And routing is one of its most critical functions. We've seen a couple of classes of routing protocols. Link state and distance vector routing. Link state is a global routing protocol, distance vector is a decentralized routing protocol. Global means you have the entire view of the network. Decentralized means you only have the view of your immediate neighbors. You know the existence of other nodes, but you don't know that you can do topology for the rest of the network. These routing algorithms, link state, distance vector start routing algorithms that compute shortest paths, both of which compute shortest paths, they are used in individual networks. So AT&T might be running a link state routing protocol in its network. Smaller networks might be running a distance vector routing protocol. On top of all of this, there is a single routing protocol for the entire internet. The entire internet, network of networks, there's about 50, 60,000, this number keeps increasing. These are called networks or autonomous systems. Sometimes the word ISP is used interchangeably, but one of these networks or autonomous systems may or may not be providing internet service to other people. But often those terms are interchangeably used. And there's about 60,000-ish of them. They run one protocol. That's called the inter-domain. So network, domain, autonomous system. Sometimes when I speak, these terms are somewhat overlapping. And there's one top-level routing protocol that holds the entire internet together. That's called the Internet's inter-domain routing protocol. Its name is BGP, Border Gateway Protocol. So in the alphabet soup of protocol names you've learned, this is maybe the top level thing that holds the entire internet together. Okay. You have done some slide. Well, that's not related to BGP anyway, so you didn't miss very much. But let's look at a summary of link state and distance vector before we move on to inter-domain. Well, I'll also spend starting the last 5 minutes in class and reading and going beyond 5-10 minutes until the next instructor comes. Whoever wants to sit can sit, answering the project 2 questions. This is due fairly soon, right? Which I should write down, because I usually write down those things. Okay, can you see this? The thing is not working. It is working. Also, homework 5 is posted. This is the last of the required homeworks. And okay, so here's a wrap-up comparison of link state and distance vector. What are these protocols? These are used in individual networks. The inter-network protocol is BGP, which we're we're going to see shortly. So what are the trade-offs of link state and distance vector? Well, you know the global and decentralized aspect. Let's look at some asymptotic metrics of complexity, right? So we've seen message complexity in link state. If you have n routers, you're looking at disseminating link state information. See, these are textbook slides. Order n squared is correct. But order n squared means grows no faster asymptotically than n squared. But a better real-world estimate for real-world protocols is order number of edges. Okay, that's what is the amount of message complexity needed to disseminate a link state information, some change in the link cost to all the nodes, right? So that's why it's already, if a message traverses every link in the network, then it's reached every node in the network. Distance vector's message complexity it's non-trivial to calculate, okay? We've seen operationally distance vector is a little bit complicated. So we saw in this example that in this tiny little network, 3 nodes will take 44 iterations to converge. We saw at the end of the class why nodes Y and Z will keep ping-ponging with each other, thinking the other node has a low-cost route until they both realize that they have to both go clockwise. In this example, it might seem trivial for Z to simply tell Y, oh, my cost of 5 is actually through you, so don't think your cost is 6 through me. That is something that seems very trivial for Z to tell Y. Not doing that is the reason this takes 44 iterations to converge. If you don't see why it takes 44 iterations, we start at the end of the class, go back, look at the textbook, right? But it's very easy to extend this example from cycles that are just, length 2, or really just, that's the cycle morning. If you just make this cycle so it's like this, at that point, even if Z was using a route through Y, it could be using Z, W, Y, and then going to X. And even if Z told Y that I'm going to somebody else, not through you, the same problem can occur. The essence of the problem is a decentralized view. They don't know the topology, they only know their immediate neighbors. Okay? So the amount of convergence time of a distance vector protocol here clearly depends on the link weights. If I made that link weight from 60 to 900, it's going to take hundreds of iterations for this network to converge. It depends on the link weights, not just the number of nodes and number of edges in the graph. So in general, it's hard to really say how long a distance vector routing protocol will take to converge unless you know some information about link weights. So some distance vector protocols bound link weights to a maximum value. They say this is infinite, okay? 16 is infinite, for example, in RIP, which is a somewhat outdated distance vector routing protocol. Cisco has a protocol called EIGRP, and that has another bigger number as infinite. That is, distances cannot go. Link weights and distances are not allowed to go beyond that. To prevent these kinds of count to infinity problems, right? Infinity is defined to be a small value. There's no cost greater than that. This is also another reason why distance vector protocols are using smaller networks. Large backbones spanning a country or a continent, tier 1 ISPs, they don't use distance vector, they use link state protocols. So, long story short, convergence time really depends on the protocol. In particular, it depends on the link weights, not just the topology. So it's hard to say in terms of N or E what the complexity is. Speed of convergence, again, it's order n squared, but Dijkstra's algorithm at an order D is going to take you only order n log n, or no greater than n log n, asymptotically. Likewise, we've seen already messages, that's order E really, also order n squared. That's the speed of convergence. So the speed of convergence relates to messages. If messages can keep ping-ponging and taking many iterations, it'll take commensurately more time to converge as well. Okay? They have different robustness characteristics. In link state routing, if something goes wrong in the network, say some router has a misperception of the cost of a link, the link is down, the link is up or the other way around, or it thinks the link cost is high, but it's low or the other way around. All right, in a graph, you have one link's information incorrectly disseminated to the rest of the network. So it's going to have a limited effect on the performance or reachability between pairs of nodes in the network. In distance vector, however, you have a problem. If some link cost, let's say, becomes abnormally high, we've seen that bad news takes a really long time to propagate and to steady state. It can take a really long time to converge. And it's also easier, it doesn't happen through manual error, administrative configuration errors, it can happen through just bugs, for example, in code. It can simply happen because of misestimations of some link characteristics. Right? So these errors can propagate through the network, and it's really hard to track what's operationally happening in this network. The key strength of distance vector is it's trivial to implement, right? Just Bellman-Ford. It relies on the Bellman-Ford equation by doing this Bellman-Ford assignment operation until it reaches the Bellman-Ford equality. But that comes at a cost of operational complexity. Okay. That's the summary of link state versus distance vector. These are intra-network or intra-domain routing protocols. Okay. These are technically correct terms. ISP is technically not the same thing as an AS. AS stands for autonomous systems. Okay, so that's the next thing we're going to look at. Before we look at, we're going to look at a couple examples of real-world examples that we haven't looked at. Just a couple of slides. An example of a real-world intra-network routing protocol, a widely used real-world protocol is OSPF, which stands for Open Short Spot First. It's an open protocol, so Open Short Spot First. It's a link state. I think OSPF is added something to the slides that is making this bulletin consistent with what's coming next. Anyway, we'll see OSPF in a second. It's coming further down. We'll continue with inter-domain routing, which is the inter-network analog of this. There's only one such protocol in the network. So what are the goals of an inter-domain routing protocol, or this BGP protocol that happens to be the internet's so-called de facto routing protocol? Okay. There wasn't an explicit conference of all ISPs coming together and deciding we're going to pick this protocol as our common worldwide single internet protocol. It just, ISPs started speaking it, it became the de facto protocol of the internet. Okay. It's gone through a few revisions over the last 3 decades or so. It is what's holding together billions of end hosts, millions of routers, and tens of thousands of these networks or ISPs. So you want, what are the goals? You want 2 things. Scale. Okay. It should scale to a large number of ISPs and routers. And it should allow for administrative autonomy. UMass is an autonomous system. AT&T is an autonomous system. UMass is, of course, a much smaller geographic network than, say, AT&T or Verizon. But these are organizations or companies that have autonomy. They have control over how they run their affairs or their business if they're a for-profit corporation. So we want companies to be able to decide how they want others to route to them, and how companies or networks decide how they want others to route to them, and how they will choose routes to get to the rest of the network. That's administrative autonomy, and that's why these networks are also called either domains or autonomous systems. Okay? So those are high-level goals. In the internet, every single one of these networks or domains has an intra-AS routing protocol, like a link state or distance vector, and there's only one inter-AS routing protocol. Some routers in each AS are called border routers or gateway routers. Border routers, gateway routers often are used synonymously. Gateway is a term also just used sometimes synonymously with a router. But in this context, if you're seeing a gateway, it's generally at the edge of the network. So, let me show you a pictorial example. So that's right there. It shows you 3 networks or 3 autonomous systems. Some of these routers are edge routers, so routers like 3A, for example, or 2A, 1B, 3A, these are edge routers or gateway routers. They're not the only routers that speak that inter-domain routing protocol. All routers will, gateway or border routers will not will speak this inter-domain routing protocol. What's happening with these, at these routers that's feeding into the forwarding table? What's the router, how are these routing protocols interacting? Well, within a network, each router is running 2 routing protocols simultaneously. It's running a routing protocol like a link state or distance vector to find routes to shortest spots to other routers in its own network. Additionally, it is also running an inter-AS routing protocol that is at one level higher than the intra-AS routing protocols. Both routing protocols coordinate or combine to generate the forwarding table and forwarding behavior or the data plane behavior at every single router. There's contributions from both. Okay? If a router is trying to know, or in this case, let's say 1A is trying to know how to reach 1B, then it can just rely on the intra-domain routing protocol. But if 1A is trying to know how to reach 3C or 2B, it has to run on both protocols, not just both intra and inter-domain routing protocols. Okay, so that's what we're going to see, how the two are operating together, conspiring to generate this forwarding table information to both intra and inter-AS routing components. Okay, so for external destinations, not in your own network, it's not like intra tells you routes to destinations within a network, inter tells you routes to destinations outside. The former is true, the latter is not accurate. For destinations outside the network, both protocols combine to tell you what your forwarding behavior should be. Alright, so let's look at inter-AS routing, the important components of inter-AS routing. In this example, suppose AS1 receives a datagram that is destined to, so AS1 is the middle AS, it receives a datagram that's destined to some router outside of AS1. Okay, what is it going to do? The router knows that it should forward this packet, this router knows that it should forward this packet to a border router, to some border router in AS1. Okay, it has to get it outside of its network. But the question is which one? Should it go to 1C, that is clearly a border router that's peering with AS3, or should it send it towards 1B, which is peering with AS2? In this example, those are the only 2 ways to get out of your own network. And that's the question this router needs to answer. So AS1's inter-domain routing protocol needs to satisfy these 2 objectives. One is to learn from adjacent AS routers which ASs are reachable through them. Second is to internally propagate this information to all the routers within your own. So for example, 1B will, 1B in this network will figure out from AS2 which networks or which destinations are reachable via AS2, and then it'll propagate internally to 1A, C, and D this information that, hey, these are the prefixes that are reachable through AS2. So if you have packets that are destined to any of the prefixes reachable through AS2, send it towards me. All right, so that's how both of these tasks, gathering outside reachability information and internally propagating it, these are both part of inter-AS routing. Okay. So what are the most common intra-AS routing? We'll start with the intra-AS routing. So this is the high-level overview of inter and inter-AS. We'll now look at examples of intra-AS routing protocols, like OSPF, RIP, and so on, and then we'll look at BGP. There's only one intra-AS routing protocol, okay? So there's no variety at the intra-AS level, unlike the intra-AS level. Let's start with the intra-AS level, real-world protocols. So examples of link state and distance vector. These are some of the most common links, distance intra-AS routing protocols. Both of these are DB, distance vector based. So RIP is an example of a distance vector routing protocol. It's not very widely used, but RIP makes a few adjustments to distance vector as we learned it in order to mitigate some of the problems like counter infinity. So we saw this counter infinity problem in the triangle network, right? RIP says in order to mitigate those kinds of problems, all hop counts all link weights are hop counts. So every edge is a weight 1. And infinity is 16. So a network has a diameter of greater than 16 hops. Any pods of greater than 16 hops, well, it's not allowed. So it's used only in small networks. So the amount of count to infinity style problems that we saw in the triangle network, those are highly mitigated just by restricting it to small networks, making hop count the metric, and saying 16 hops is the most the network can have. EIGRP isn't quite as simplistic. It used to be a proprietary routing protocol, but for a few years now it's been an open protocol. It's also distance vector based. It allows more flexibility than hop count, but it's not easy to fix these count to infinity style problems. There are some hacks you can do to mitigate that effect. So what you can do is you can say in the triangle network you would say if I'm taking a route through my immediate peer, then I'm going to advertise a cost of infinity to that destination with the immediate peer because I don't want this cycle. But that doesn't break cycles longer than 2, right? So even any distance vector routing protocol, including EIGRP, which is a little more sophisticated, fairly more sophisticated than RIP, doesn't fundamentally solve that problem of count to infinity. OSPF is an example of the most common, widely used link state routing protocol. This is the protocol that's used in large ISP networks. So tier 1 ISPs, big regional ISPs, they're all likely to use some variant of link state routing, OSPF being the most common one. ISIS is an example of another shortest path, link state style shortest path routing protocol. Happens to be, it's essentially the same, but it's not an RFC standard, so it's not, it's not an open RFC-based routing protocol, but it meets what's the ISO standard, which is a minimum set of requirements that any of the protocols operating on the internet protocol stack should obey. It's also a Cisco protocol. It doesn't say that here. So let's have a quick look at OSPF. That's the only one of these 3 protocols where there's at least one non-trivial element beyond the conceptual stuff that we've already seen. It's really just Dijkstra's algorithm, okay? But it's a little more than Dijkstra's algorithm in practice. So OSPF is open. It's open source, that is. It is a classic link state routing protocol. It's based on flooding link state advertisement. One thing we'll focus on here is what are the protocols they're using? What transport protocols are they using to send messages? Even with adjacent neighbors, you got to send messages to adjacent neighbors to flood link state information you're sending to your neighbors. What is the protocol? Are they using TCP, UDP style protocols? What protocol are they using? Well, the answer in the OSPF case is OSPF is not using a transport protocol like TCP. It is an application level process. A routing protocol runs as an application in that machine. However, it's not using a traditional transport protocol. Instead, OSPF runs directly on top of IP. So OSPF is its own protocol. It'll have its own header on top of IP. It's not using a transport. You can think of OSPF itself as its own transport protocol. Those metrics, I told you, the link weights, you can configure them to a variety of metrics. They are based on lowness of bandwidth or highness of data. High delays are bad, low bandwidths are bad. You can also combine these metrics into a link cost. We'll see a little bit more about how these link costs are used when we look at traffic engineering. And we already know that in linked state routing, each router has a full topology. You need a full topology to run Dijkstra's algorithm. So this is all fairly straightforward. OSPF additionally has some support for security, so message authentication. Similar to SSL, like when you use HTTPS, what are you getting? You're getting authentication. You're getting the guarantee or assurance that the entity you think you're talking to is indeed the entity you're actually talking to, right? So in a network, it's your network, all the routers have the necessary authentication information, the certificate information. You bootstrap them with that information so you can authenticate this on at runtime. If not, anybody can, if they can plug into any portion of your network, they can infiltrate your network with messages that are unauthorized, and that can happen. They can bring down the network. So the one non-trivial architectural element in OSPF is its support for hierarchy beyond basically Dijkstra's algorithm, right? It's used in large networks. We saw that it has order n squared complexity. Even if you say that it's n log n for the computation, and even if you say message complexity is really order number of edges, if you think about it, in the worst case, the number of edges could be quadratic in the number of nodes in the network. Every pair of edges could have a link. In that case, okay, number of edges could be order n squared, right? And so in large networks, this can be a problem. In order to manage the scale, in order to avoid this up to order n squared message complexity, OSPF breaks down large networks into a backbone network and area networks. So there's a link state routing protocol just for the area networks, and then there's one link state routing protocol for the backbone. And there's really only one way to go from one area to the backbone. So if you want to go from area to area, you go through the backbone, right? There's not much of an option to do that. So this hierarchy, the n in each region or the backbone becomes much smaller. So the total complexity becomes n1 squared, n2 squared, plus n3 squared, and so on, instead of n1 plus n2 plus n3 the whole square. They're using hierarchy to address scale in practice, and OSPF has support for this kind of area summarization and a separate backbone routing protocol. But they're all using Dijkstra's algorithm, so that's sort of the essence, the conceptual essence of what's happening. They're all global routing protocols. Okay. That boundary router, that's the router that's going to be speaking for the interdomain routing protocol in addition to this OSPF. Okay? Let's look at some technical questions real quick before we go into take 20 seconds. Everything done? Okay. The answer is right there. So the question, what is the tightest bound? It is, I told you previous class as well, order, big O notation, is an asymptotic upper bound. So if you say something is order n squared, it is also order n cubed, it is also order n to the 4. So if something is order n squared, you don't know if it's order n or n log n. O, big O means bounding it from above, right? The complexity, if you want the tightest bound in the message complexity of reacting to a single event, that is simply in link state routing, the complexity of disseminating that information to all nodes in the network. The tightest bound is the number of edges. If you send a message on every single edge on the network, because it's written here, and this is exactly what I told you a few minutes back and at the end of class as well. So order n squared is not the tightest bound. it is also order n squared. Order E is order n squared too. The number of edges cannot be more than quadratic in the number of nodes in the network. So the right answer is B, okay? Okay, so I think there were 85-ish or so, I forget the exact number, but I'll wait till 17 students have quick answers and then I'll count down. Okay, 5, 4, 3, 2, 1. I see some people switching over to. Right, so there you go. It depends on many ways. Okay. Each node does not know the entire topology. Why does it depend? That's the essence of the counter infinity problem. The dependence on link weights is why it can take, convergence can be really hairy. Understanding operationally how it's behaving. Okay. Distance vector, roughly how many iterations will the topology and link class change to converge? Okay, I think we're out of time. 5, 4, 3, 2, 1. Let's see. I think people are just taking random guesses here, right? Because, well, I know this. Distance vector routing's counter infinity is not an easy problem to wrap your head around. Okay. We saw why this happens in the previous class. So it's clear that this is just random guesses, but I'm going to take one more shot at explaining why it happens through this other example. So hopefully you'll be able to answer a homework question that's more than 3 nodes. Okay, it gets much hairier if it's more than, even in a 3-node network, if it's more than 3 nodes. Okay, so what's happening here? X, Y, and Z. Okay, those are still, we still have the same instance. The link cost is changing from 4 to 200. Just before that bad event happened, it's clear what the routes were. X was taking, Y was taking the direct link to X, and then Z was taking the route through Y at a cost of 6. Okay? Obviously nobody wants this cost of 80. So much is obvious, right? Yes? I'm not getting enough affirmative noise. Makes sense. What is X's distance vector in the beginning? The distance, and let's say X is node 1. The first node, Y is the second node, Z is the third node. Okay, so those are the indexes in your distance vector. Initially, at bootstrap time, X thinks its distance to itself is 0. Let's assume that this network is converged just before the bad event happened. Just before the 4 to 200 cost increase happened, X thinks its cost to itself is 0. X thinks its cost to Y is 4. X thinks its cost to Z is 6. Okay? The network's at steady state just before that event happened. Nobody wants E. What is D of Y? Can someone tell me what D of Y is? Distance vector of Y. Yeah?
402.
Good. Okay. Okay, that's D of Z. just before this bad event happened, the increase from 4 to 200. This should be obvious, right? The Bellman-Ford equation is satisfied here. You can see that for every node, if it takes the minimum across all of its neighbors, the cost to get to its neighbor along the direct edge, and plus the cost from that neighbor to get to any destination in question, that will be its shortest distance to that destination. Correct. What happens when 4 goes to 200? Let's track what the distance is to the destination x, how they change at y and z respectively. We'll focus on that, because if we focus on all the distance vectors, even in a simple network, it's going to get really hairy. Okay? We're focusing on the destination x and ask how y and z's perception, so how dxy, y's perception of the least cost distance to x, and dzy, dx, z's perception of the x element of its distance vector. So this element was initially 6, and this element that was initially 4. We're going to focus on how these two change over time as soon as that event happens. How are they changing over time? As soon as y detects that 4 has gone to 200, it is going to still be getting this distance vector from z. Okay? It's going to see that, oh, my direct link is now 200. Okay? I'm no longer going to take my direct link, which was earlier 4, because now it's become 200. But z seems to be announcing a distance of 6 to get to x. And I can get to z at a distance of 2. Therefore, I might sound dumb, but I think I must be able to get to x at a distance of 2 plus 6. So I can get to z, I is y here, I can get to z at a distance of 2, and z seems to be saying it has a distance of 6 to x. Therefore, I must be able to get to x at a distance of 8 by going through z, which of course is going to return the packet right back to me, but I'm dumb because I'm decentralized, I don't have a global view. So now, this has gone from 4 to 8, and y is going to announce it to both neighbors including z. Z is going to look at this 8 distance to x and say, okay, y is saying my direct cost is 80. Y is saying it can get to the destination at a cost of 8. My cost to go to y is 2. Therefore, I must be able to get to x at a cost of 10. 8 plus 2. I go to y, and then y is saying it has 8. So it starts announcing the cost of 10, at which point y is going to do what? What should I write here? Yeah?
I think it's right 12 because y is going to c and taken 10 that is required for z to get to x.
Yeah, so what's the number here?
12.
12. Good. What comes here? Yeah, so that's how it's increasing. The 4 is no longer relevant, okay? Or sorry, is it? And this announces 12, yeah. Z is just going to be adding, yeah, 4 is becoming irrelevant at this point. They'll keep jumping by 2 until what point? Until a point when if dz ever becomes greater than 80, z is going to say, oh, my direct link is 80. I'm not interested in going through y anymore. Okay? So that's the number of iterations you're looking at. And that is about, so if you can't start counting from here 1, it's increasing by 2 every time, and it's going from 10 to 80, so about half of 70, and so the closest answer is 36. Actually, that's the first iteration, so if you count both, it will be exactly 36. After one iteration, you're here. After, not 36. After one iteration, you're here. After the second iteration, Z will update. After the third iteration, Y will update. After the fourth iteration, Z will again update, and so on. So it's twice that, and therefore the answer will be 75, which incidentally happens to be the Mohn answer, which is good. Okay? I don't know how many people actually did this math, but that's the math that's happening. Oh no, sorry. So it's not the Mohn answer, but very close to the Mohn answer. So 75. Okay? So that's how we got 75. The number of steps here, 8, 10, 12, 14, 16, and so on. That's until this crosses 8, at which point we all take the clockwise out. Okay? Questions on this? Alright. So that's about link state and distance vector routing protocols. There is a variety of link state and distance vector routing protocols, but there's only one inter-domain routing protocol, and this is called BGP or Border Gateway Protocol. That's the protocol holding together the 60,000 odd autonomous systems that power the internet. BGP has two components, eBGP and iBGP, that respectively cater to its two fundamental goals. From neighbors, learn what destinations, neighboring ASs learn what destinations are reachable. Having learned that information, propagate it internally inside your own network. That's the iBGP. External BGP and internal BGP. Okay? So let's look at pictorially how this is working. So this shows you eBGP and iBGP connections between routers. Any connections between border routers or border gateway routers, those are eBGP links, eBGP sessions. What is an eBGP session? It is just a TCP session. We said OSPF runs on top of IP. OSPF is its own transport protocol. It doesn't use TCP or UDP. BGP, however, uses TCP as its transport protocol. BGP can also be run over long links. Sometimes they even run over virtual pods instead of links. So TCP gives you all the reliability stuff. It comes in handy, so you don't have to implement reliability like you're implementing in Protocol 2. You learn that it's non-trivial to implement reliable transport protocol. TCP exists, right? Okay. So BGP's transport is TCP. It's advertising, it's learning through eBGP sessions what destinations are reachable from adjacent ASs and propagating through iBGP internally inside its own network. So let's say this is a prefix X. This could be, let's say, 128.119/16. This is a prefix that belongs to UMass. How does UMass's reachable, how does the world, how does Princeton or how does Deutsche Telekom, its customers, how do they know how to reach UMass? This information is being propagated through BGP to the whole world, to all of the autonomous systems in the internet. So AS3, let's say AS3 is Sprint. Sprint is one of UMass's providers. AS3 is saying, hey, if you want to get to UMass, which is X, send packets this way. It's announcing reachability to UMass to its adjacent ASs. When this border router speaking eBGP over TCP, right here, when it gets this advertisement that X is reachable through AS3, it is going to internally propagate this information within its own network. And this information, after that, is going to be further propagated from 2A over to AS1, saying X is reachable via the path AS2, AS3. So here, all the routers know that X is reachable via this path AS3. When this route, when it goes through the network and then re-advertises it to the adjacent AS, routers in AS1 know that the path AS2, AS3, X is the way to reach X. Unlike link state and distance vector routing protocols in BGP, the entire AS path is sent. you don't just send a cost or anything, you send the path. You say you go through these AS numbers to reach X. So what are the routes? In every advertisement, implicitly is a promise to say, I will follow this route to reach this prefix. And anybody who receives it can adopt that route and then further repropagate that route into its internal routers as well as its upstream routers in adjacent ASs. So routes go through eBGP, IBGP, eBGP, IBGP across different networks, and the entire AS route propagates all the way. That's how BGP is working. What are the properties in these routes? These routes carry a bunch of information, of which these are some of the most important pieces of information. Every route will carry a prefix, the destination that is in question. The route is to reach some destination. And these are two of the more important attributes. These are not the only two attributes. AS path and next hop. AS path is literally what it says, AS path. So AS43, AS21, AS19, and then X. That's a route that is being advertised in these BGP advertisements. It's saying you go through AS43, AS21, AS19, and go to X. That's your AS path. Next hop is a specific internal AS router to get to the next hop AS. Okay, so when, go back to the previous slide. In this example, 3A is advertising the route AS3X to 2C. This interface is the next hop, not this interface, this interface. AS3 is saying, I can get to X through this interface. And so any router that wants to get to X through AS3 has to make its way into this interface, right? So that's the next hop. BGP is called as a policy routing protocol. Link state routing and distance vector routing intra-AS protocols, they're called shortest path routing protocols. Link state and distance vector are just two different ways to compute shortest paths, but they're both shortest path routing protocols. Inter-domain routing is not shortest path. Inter-domain routing is not trying to give you short paths, low delays, and good performance. What is inter-domain routing trying to do? It's trying to ensure reachability first. And additionally, it is trying to optimize some metric. It's not performance or shortness of path. What is it? What is inter-domain routing trying to do? What might it be trying to do if it's not trying to give you short paths? So one thing that you'll notice if you have access to a bunch of machines and you do a bunch of pings, one thing you'll notice is that if you ping from UMass, I don't know if these ping values are correct, but this can happen. It's very common. Let's say UMass to MIT is about 8 milliseconds or something like that, right? And you ping from UMass to, let's say, Berkeley. This might be, let's say, 80 milliseconds. You might find that if you send a packet from UMass to MIT, a machine at MIT, let's say you control it, and then have that machine send a packet, forward the packet to Berkeley, this entire delay is less than the direct path 80 milliseconds. It could be that this is 8 and this is just 62, let's say. So 62 plus 8 is just 7. So this is what's called as a violation of a triangle inequality. In a triangle, the sum of 82 sides is always strictly greater than the third side. This is not true on the internet. Sometimes you can go to some other place and go from that place to the final destination. You might actually have a shorter path that way. So this is an example. Triangle inequality violations are an example of why the internet's top level interdomain routing protocol is not trying to optimize shortness of your paths. That's not its first level objective. It's not trying to give you bad performance, okay, of course. But that's not what it's primarily trying to do. It is a policy routing protocol whose objective is first to make money for these corporations. These networks, domains, autonomous systems, most of these are for-profit entities that are in the business of either making money by providing service to their customers or other networks, or to their own customers. Like UMass is an AS, UMass is trying to reduce its bills. Same thing, reduce bills or make money, depends on. UMass doesn't charge us money for internet access, or sort of indirectly does through tuition and all that. But it's trying to minimize its bills, and it's using policy, which is rooted in economics, to determine which routes to take. Performance is a secondary concern. In a single network, performance is the primary concern. Shortest paths is literally trying to give you short paths in a graph. At the interdomain level, that's not happening. Policy is happening. When you get a route from more than one place to get to a destination, you're going to apply an import policy to decide which route I'm going to pick. Do I want to go through this AS or do I want to go through this AS? Which one costs me less? UMass is going to ask the same question. UMass has 3 providers. One of them is Sprint. It's a commercial ISP. The tier 1 ISP charges money to UMass. It has another provider called Internet2 or Abilene, which is a research and educational network that's free. Okay, it's government supported. So if UMass wants to go to Princeton, Princeton is very conveniently reachable through Internet2. Why would it pay money to Sprint to go through Sprint when it can just take Internet2? Costs lower. So that's an example of an import policy that tells UMass which route to take if it has more than one route option. Likewise, UMass is not re-advertising these routes to other ASs, but in general an AS, I told you, is going to re-advertise some of the paths that it learns. So I have an animation for that. So an AS, I told you before that these routes propagate internally through IBGP and then get re-advertised beyond that to adjacent ASs. So here AS2 is telling AS1, I can go to X through the path AS2, AS3, and X. So in this case, you have, in this example, you have AS1 has only one way to get to X. But in general, you might have more than one way to get to X. So in this, this slide now, AS1 can either go directly go through AS2 and then go to AS3 and then reach X, or it can directly go to AS3 and then reach X. It has 2 different ASs that are advertising reachability to X. Which one does it choose? That will depend on what commercial arrangement it has with AS2 versus AS3. AS1 and AS2 might be peers, where they say, oh, let's not exchange any money for any traffic that interconnects our customers. So it's free. If so, it'll pick AS2. It's also possible that AS2 is a customer of AS1, which means AS2 actually pays money for any traffic that flows between AS1 and AS2. Doesn't matter which way it flows. Upload, download, direction doesn't matter. When one AS is a customer of another AS, customer always pays the provider. UMass is a customer of Sprint. My home is a customer of Comcast. My home network is of no value to Comcast. I pay Comcast no matter I upload or download. Okay? My home network is not an AS, but UMass and Sprint are examples of ASs. So if you have 2 routes, one of which costs you money, the other you make money, it's very obvious which route you're going to take. So if you have a customer route, a route through a customer who's paying you money for any traffic you're going to send through them, you're obviously going to prefer that to one where no money is exchanged, or worse, you pay money. So these drive import policies. Which route you choose, which route you import, depends on which route are economical. Which route you export to adjacent ASs, or whether you export. Will this AS even announce this route to an adjacent AS? That's called the export policy. Sometimes an AS may say, all right, sometimes AS2 might say, all right, I know how to use AS3 to get to X, but I'm not going to re-announce this route to this guy. My export policy only allows me to re-announce it to a certain class of ASs. So import policies determine which routes you adopt yourself among the ones received. Export policies determine whether you're going to re-announce that adopted route to receive ASs or not. Okay? So in this example, if you have these multiple route options, then you're going to use that AS1 routers are going to use their import policy to determine which one of the two to select. Okay? So these are, I'm going to skip over the BGP messages slide and go and show you how BGP or inter-domain routing and intra-domain routing both interact to generate forwarding table entries. So in this graph, AS1 has two options. You can go through the direct AS2, or you can go through the direct AS3X route or AS2 AS3X route. So let's look at some router in this network AS1. Okay? So if you look at router 1A or 1B, or let's start by looking at 1B. Its forwarding table is going to look like destination and outgoing interface. 1B through the intra-domain routing protocol, like OSPF, for example, knows that to reach 1C, it has to send the packet on interface 1. Okay, it knows that through just the intra-domain routing protocol. For external destinations, we need additionally, in addition to intra-domain, we also need the inter-domain routing protocol. How does that work? Well, let's look at X. X is an example of an external destination from 1B's point of view. 1B is going to say, any packets destined to prefix X, I'm going to send on the outgoing interface 1, because that is the way for me to reach 1C. And to get to any place outside my own AS, I have to go to 1C, my network's border router. In this example, that's the only way to get out of my network. Right? So in this example, the route to prefix X, which is in a third-party AS, at 1D is determined by a combination of inter-domain routing protocol plus intra-domain routing protocol that says, I first get to my border router and then take the route, the most preferred route from there on. Okay, so this is an example. Let's look at one more example of an internal router, router 1A. At router 1A, it has this entry that says, to get to 1C, my border router, I'm going to take interface 2. I think the interface should be numbered. It is numbered. So that's your interface 2 to get to router 1C. And to get to X, also I'm going to take interface 2 because that is the way I get to 1C. All the routers in this example first get to 1C in order to get anywhere outside. But in general, you could have more than one option. Here, they all have to go only to 1C. So it seems like there is no real other option. But in general, there might be more than one option to get out of your network. And there you have a choice to make. So I'll shortly show you what the choice is after showing a list of common BGP import policies. If you have multiple route options, I told you import policies determine how you select routes. What are examples of import policies? Well, I already told you, the routes that make me money are more preferred to routes that neither make money or neither cost money, that are more preferred to routes that cost money. Those kinds of preferences are captured by the highest order metric. That's boringly named local preference. It's configured by operators so that it's configured by operators to prefer customer routes over peer routes over provider routes. Customer routes make money. Routes going through a customer will make you money. Peer routes is between equal. The two networks say, oh, we both have value by interconnecting our networks. Our customers can quickly get to each other, so let's not exchange any money and call it a wash. With providers, you cannot negotiate that way. You get much more value, reachability value to the rest of the network, so you agree to pay them money. What negotiations happen between ASs, these are just business transactions. They're not necessarily public. But you can infer a good amount of it. Those kinds of preferences are all captured by the first metric, local preference. So the number one metric of the routing protocol in the internet is a policy that's based on economics. It is not trying to optimize the shortness of your pods or the fatness of your pipes, bits per second or seconds delay. The number two metric is one that sort of relates to performance. It's not like they're trying to be evil. They're not trying to give you long pods. The number two metric is if you have multiple options, the route that goes through the fewest number of ASs is the route that will be more preferred. That's strictly lower in priority to just an operator configured local preference. Shortest AS path, shortest number of ASs doesn't necessarily mean shortest ping delays. You may traverse two ASs in one path, but these two ASs might be like national or intercontinental size tier 1 ISPs. They may go a long way to another continent. Another path may go through 4 ASs, but still might be in the United States. So it might be shorter in terms of ping delays, it might be better for TCP performance from every metric you can think of. But shortness of ASs, you can say, is sort of one type of a loose proxy for some notion of goodness of performance, for shortness, right? But it's not necessarily short ping delays. This is not the exhaustive list of all preferences. There are some very common ones that are in the order of priority. After these comes one called multi-exit discriminator. Multi-exit discriminator is in one AS telling another AS through which next hop that it's advertising should it send traffic. So let's say Sprint and AT&T peer in Boston and in SF. So they have routers that speak EBGP in two cities, Boston and San Francisco. And let's say Chicago. When Sprint might tell Boston, Sprint might tell AT&T, I can take packets from the East Coast to the West Boston to SF right here through our router here. So send me packets at this router. Or it might advertise to AT&T saying send me packets at this router. Or I'm not going to ferry your packets across the country. You do your job to get to San Francisco and then give it to me at San Francisco. So that exit discriminator, that's part of the BGP route advertisement. That's one AS telling its adjacent AS, if they have multiple places where they peer, which of those exits for you and entry points for me is more or less preferred. The receiving endpoint may or may not take that advice. It may decide, okay, if you're carrying my packets, I'm going to give it to you at Boston. I don't want to drag it all the way west. Whether it's respected or not, again, depends on what the local policy is. A very important policy is one called early exit that really drives home the point of how inter and intra-domain routing protocols work together. Early exit routing is also known as hot potato routing. Okay, what's it called hot potato routing? The idea is that you want to get it out of your network as quickly as possible. If you ever held a spud right out of the oven, it's not easy to hold it for very long. You want to throw it away as soon as possible, right? So that's the imagery to keep in mind. Hot potato routing, a packet is like a hot potato. If you can get it out of your network as soon as possible, that's the best option. So here's how it works, and this also is the best illustrative example of how intra and inter are both working in coordination to determine forwarding behavior. So in this example, AS1 again, like before, has multiple ways. So if you focus on router 2D, Oops, sorry. In this example, router 2D is learning. So this is router 2D. It's learning via IBGP that can route to X either via 2A or via 2C. So it can go like this and go reach X, or it can go like this and reach X. So here's a concrete example where there are two different border routers that it could send packets to in order to reach X, and they're both actually going via two different ASs in this example. Which one does it pick? Well, here hot potato routing will say, pick the gateway router in my router that gets the packet out of my network as quickly as possible. If you look at link cost here, 201 is less than 263. So OSPF, the intra-domain routing protocol, will tell that router that the best way to get this packet out of the network is by going through this 201 link. That was determined by OSPF. So 2D's forwarding behavior to X is determined by a combination of inter-domain routing and OSPF pathways. They're both combining. One is not enough to answer this question. Okay? This is also a reason why two different routers in the same AS may take two different AS level paths. So 2D might decide to go like this, however, 2B might decide to go like this. So 2D is taking the route AS2, AS1, AS3X, but 2B is taking the route AS2, AS3X. Two routers in the same AS may take different AS level routes to get to the same destination because some of their forwarding behavior is determined by the intra-domain routing protocol. Okay? Let's look at some more examples. Let me stop for a second. We've been talking for a while. Questions thus far? Homework questions are based on this, okay? So let's make sure we understand the economics aspect of this. That's really crucial. What determines whether you pay money to somebody, you get money to somebody that you peer with, or it's a wash, you neither pay nor get money from them. These are based on economic transactions. These are based on who gets value by connecting to who. For my home network connecting to Comcast, it's really clear who's getting value, right? But in other scenarios, it's not so obvious who's getting value. That's determined by the marketplace. So for example, let's say this is Sprint. This is UMass. And let's say this is Smith. And let's say Sprint provides internet service to both UMass and Smith. They both agree to pay Sprint. Generally, these agreements are the kind, if you send these many gigabits of traffic per month, at the end of the month, we're going to pay you this much. It's not a fixed price, $40 a month like internet service, right? It's based on a massive amount of traffic that's going on a monthly basis. So the more we guys upload and download, the more bandwidth bills UMass is incurring, okay, with its ISPs. So dollars always flow this way. Doesn't matter whether these people are downloading or uploading. At some point, UMass and Smith people might get together and say, hey, we're like the 5 college people, we're all academics, we're friends. For my people to talk to your people, we're paying money in 2 steps to Sprint. We're paying money here, we're paying money here. Seems like a waste. Why don't we just run fiber between our networks, between Amherst and town of Amherst and Northampton, and just call it a wash. We're friends. We're about comparable. We both get good value or interconnected to each other. I mean, UMass is much bigger than Sprint, but let's say they're comparable in size. It would make economic sense for them to just interconnect the networks, not charge money here. And both will save money that they're paying to Sprint to get to each other. This is called a peering arrangement. This is a customer-provider arrangement. So this is a customer-provider link, that's a peering link. In the internet, a very important kind of policy routing is one called valley-free routing. That captures export policies, that captures whether you re-advertise a route to somebody else or not. Okay, so let's say Sprint has a route to New York Times as prefix, okay, popular news site. Sprint is telling these guys, I can reach New York Times, the prefix, New York Times is prefix to UMass and Smith, so they both pay money to get there. When Smith gets this advertisement, it's not going to re-announce New York Times reachability to UMass. It is going to announce reachability to its customers, its people, local subnets to UMass. But it's not going to announce reachability to New York Times to UMass. Why should it take UMass's New York Times traffic, pay money here, when these people are not its people? Same thing for UMass. Why should UMass re-announce New York Times' route to Smith and make no money here, but pay money here? It will not. So UMass will announce these subnets to Smith. Smith will announce these subnets to UMass, and they can go, those guys can talk to each other. But UMass or Smith won't re-announce provider routes, routes learned from providers to peers. So that's an example of what's called valley-free routing, where the general principle is there's no valleys in routes. What does this no valleys in routes mean? Routes, internet routes all look as follows. They can go up, 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 up. Up means customer to provider. This is customer, this is the provider of this customer, this is the provider of this customer, this is the provider of this customer. Valley-free routes means routes always should look like any number of customer to provider links, possibly zero, followed by zero or at most one sideways link, which is peering link, no money exchanged, followed by any number, including zero, of downward provider to customer links. So here, dollars are always flowing this way. Here, dollars are always flowing this way. Here, there's no dollars. Re-advertising of routes on the internet is done such that all routes match this pattern, which is some number, including zero, this is the regular expression line, of customer to provider links, followed by one or zero peer-peer links, followed by any number including zero provider-customer links. So this is an example of a valley-free internet route. This is an example of a valley-free internet route. This is not an example of a valley-free internet route. It doesn't fit this pattern. Because once you take a sideways link, you have to come down or stop. Okay? Two sideways link, this is not allowed by that regular expression. You can keep going up zero or any number of times. After that, you can go sideways once at most, or not. And after that, any number of times you can go only downward. All internet routes look like that. And that's called valley-free routing. And that drives, that's fundamentally based on economics. So you never go like this and up. You never go sideways and up, which is the reason why Smith will never re-advertise New York Times' route to UMass, because it's not making money on one side, it's paying money on the other side, and it's doing it for not its customers. All right, so that's what's driving economics. I'll stop there. The textbook has some other examples, the slides as well, of how Galaxy routing is being done, not using up-down terminology, figures like this. How do you take questions on project 2? There's a whole bunch of questions that's already answered on Piazza. I've added a bunch of tips, so make sure you look at them. An important thing to keep in mind, give me 30 more seconds please for project 2. Not everybody may be able to pass all correctness tests. So unlike project 1A, this is harder. I think you've realized this is harder, right? As of like exactly 1 week back from now, 85% of you said you're going to start the project. Project's been out since the beginning of this month. So you may not be able to finish all correctness, pass all correctness tests. That's not uncommon. About half the class happens to finish all correctness tests. But for project Part B is much more identical to Part A than in project 1. If you didn't pass all the correctness tests, continue working on the correctness tests in Part B. The best way to get the most number of points in Part B is to first make sure you pass as many correctness tests. If you pass only 12 of the 15 or so correctness tests, and you have a total time of 300 seconds, you are still worse than somebody who passes 14 correctness tests and takes 500 seconds to finish all the tests. So correctness comes before time. So keep that in mind, that you need to continue fixing that even as you work with Part B. Okay?